Okay, so today we're going to learn new module, okay, which is a module 9. So in this module 9, you will learn about stack pointer and subroutines. Okay, so without further ado, let's look at the overview of the stack. Okay, what is the stack? Okay, why the stack is important? Okay, every time you're going to use it uh, as a subroutine. Okay, so stack is a section of RAM, okay, used by the CPU to store information temporarily, okay, which is either you're going to store data or you're going to store an address. Okay, so since the ARM processor only have a limited number of register, okay, to store the data temporarily, so you need to have another uh, storage system, which is a stack, okay, which is you can use this stacks to store any information temporarily, okay. The information can be either data or can be an address. Okay, so the CPU need this address because there are only limited number of registers. So usually a stack is a last in, first out, okay, a LIFO. Okay, LIFO buffer containing a number of data items usually implemented as a block of n consecutive bytes, words or long words in a memory. So every time you're using a stack, what happens here is the data that you're going to put in that stack, it is using a last in, first out buffer. Okay, what is a last in, first out? Whatever that came in last to that stack become the first one that will go out from the stacks. Okay, so the address of the last data item placed into the stack is pointed to by the stack pointer. Okay, so by using a stack pointer, okay, you know where is the location of the last item that is being put in the stack memory. And here are examples of application, okay, that using a stack, okay, which is the first one here is to temporarily as a temporary storage data, okay, when a function being executed and need to use a register bank for data processing. Okay, since we have a limited number of registers and maybe some of the register already have a value inside there, but at the same time you're going to use that register, and what happened here is, okay, without so what happened here, okay, since you're going to use that register and you don't want to have the original value inside of the register is replaced, okay, after you run a certain program, a certain function. So what happened, we just put this original value to the stacks. Then after that, you can use the CPU can use that register to perform any data processing or anything. Okay, once that data processing is finished, then after that, okay, you can retrieve back the original data and return it from the stack and return it back to the original register. Okay, and a part of that, okay, the stack also can be used as a temporary storage for local variables. Okay, if you're going to put any variables, okay, to store any variables, okay, you can put it on the stack as well. Okay, and the third one is passing information to function or subroutine. Okay, so again, okay, every time we're going to uh, call a subroutine, call a functions, okay, and when you're going to pass that information to the fun to the subroutines, okay, you can put it temporarily on the stack as well, and to hold processor status and register value in the case of interrupt. Okay, so you can put the processor status or any register value, okay, every time the interrupt happens, okay, which you put it on temporarily on the stack. So this is the application of stacks. Okay, so in Cortex M, Okay, so the Cortex-M use a stack memory model called a full descending stack. Okay, what is a full descending stack? When the processor started, okay, the stack pointer is set at the end of the memory space reserved for the stack memory. So here, every time you're going to use the stack, okay, make sure that your stack pointer is pointed to the last address of your RAM. That is the ideal place lah to put the stack. Okay. For each push operation, okay, push operation means that you're going to put the data in your stack memory. Okay, so the processor is first decrement the stack pointer, then store the value in the memory location pointed by stack pointer. Okay, actually, this stack here, okay, where you might asking, okay, where is the location of the stack memory? Okay, the stack memory is actually inside of your RAM. Okay, assuming that we have the RAM, okay, this is the RAM. They started from 2000 until blah 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 blah. Okay, and your stack can be between this RAM here. Okay, you can put it. Okay, you can initialize your stack somewhere around here or here, here, or anywhere, as long as it is inside of the RAM, you know, the SRAM. Okay, ideally, okay, usually, okay, ideally lah, okay, every time if we're going to initialize our stack, okay, we need to initialize our stack to the end address of the RAM. Okay, which is your stack pointer must pointed to this address. So this is your RAM N. SRAM N. Okay, so this is the idea lah. Okay, so the stack can be anywhere as long as it is between the RAM sections, RAM region, but ideally we're going to put it on top of the or at the end address of the SRAM. Okay, so what happened here is every time you are going to put a data to your stack, okay, so let's say you're going to put the data on your stack, okay, the stack pointer will decrement. Okay, the stack pointer, the address of this stack will be decremented. Okay, so during the operation, the stack point to the memory location where the last data was pushed to the stack. Okay, so this stack pointer is actually important lah. Okay, the SP, the stack pointer is actually the important part, okay, where it point to the location of the stack, okay, where you're going to put your data. Okay, so every time you push the data, push means that you're going to put data, okay, put data in stack memory. So that's what we call as a push operation. Meanwhile, for the pop operations, okay, so the pop operation is the value of the memory location pointed by SP is read. Okay, you're going to retrieve the data. Okay, get back the data from the stack. Okay, so retrieve data from stack, and you're going to put back to your general purpose register. Okay, your RN. Okay, either R0, R1, R2. So this is what the pop operation do. Okay, so when the pop operation do, what happens here is you read the data from the stack pointer, and the stack pointer is incremented automatically. Means that every time you retrieve the data, the stack pointer will incremented. Okay, so later we'll see the examples of how the stack work. Okay, every time you push the data to your stack, okay, the stack pointer is decremented. Then when you pop the data from the stack, your stack pointer is incremented. We will be looking at that. Okay, how the stack pointer works. Okay, for examples. Okay, so this is examples. okay, of stacks. Okay, we have a memory. So this is the memory. Okay, so this is your memory. Okay, which is our data memory lah. Okay, we okay, in this case, this is our RAMs. Okay, now we're going to look at the pop operation and push operation. Okay, so this is a pop operation, a push operation, and this is for pop operation. Okay, so assume that the address here is okay, the highest address is on at the top lah. Okay, by looking at this arrow here, okay, arrow here, it says that okay, the address is highest address is on at the top. Okay, I just put the FFFFF lah. Okay, let's say this is the highest address, and the lowest, the bottom here is the lowest address. Okay, okay. Let's assume your okay, you initialize your stack pointer here. Okay, so you initialize your stack pointer in the middle of your SRAM. Okay, in the middle of your memory. So now you have a data. Okay, so this is the data. There is this data is inside of the general purpose register. Okay, and this data you're going to put it into your stack memory. So how to do it? Okay, you have the data. Okay, and this data is from, let's say lah, this is from R0. And inside of R0, you have this value 1, 2, 3, 4. And you're going to put this 1, 2, 3, 4 to your stack memory. So how this stack works? Okay, so in order to put this data R0, which is one content of 1, 2, 3, 4 value to your stack, what you need to do here is you need to use the push operation. Okay, by using the push operation, which is the push operation is push lah at PUSH. Okay, and then followed by the register name. Okay, so here what happened here? So since my R0, the value of 1, 2, 3, 4 is inside of R0. So by using the push R0, okay, by you execute this instruction here, what happened now? The stack pointer, okay, that is currently point to this location. Okay, the location that I highlighted with this blue color here. Now it decremented. Okay, why decremented? You see here on top is a highest memory address, bottom is a lower memory address. Okay, so every time you use the push operation, so what happens? The stack pointer will be decremented. Okay, so that's why it will go 1 byte or 4 byte. Okay, in the memory. Okay, then after that, you store the value from R0. Okay, you can see here, after you decremented the SP, okay, the stack pointer is decremented. Then after that, this 1, 2, 3, 4 is stored inside of this location. So this is what, so every time you do the push operations, so this is what happens. Okay, so now move on to pop operation. Okay, what the pop operation do? We're going to retrieve back the data from the stack memory and put it back to the register, to your general purpose register. So to do that, okay, you're going to use the pop instruction. Okay, pop RN. Okay, so pop instruction is used to retrieve the data from the stack memory and put back to the register. Let's say lah, my instruction here is a pop R1. So when I execute this line, okay, pop R1, okay, you see here from this memory, this is the data lah inside of the memory. Okay, so when I use the pop, what we call here, pop instruction pop R1, okay, so this data 1, 2, 3, 4, okay, will be sent to your R1, okay, your general purpose register. And at the same time, okay, the stack pointer is incremented. Okay, you see your stack pointer now point to new address. Okay, so it incremented from this memory address to a new memory address. Okay, so it depends on how many data that you're going to push lah. Okay, if you're going to push 32-bit data, means that your memory address will incremented by 4 bytes. Okay, so if you're going to push 8-bit data, so the memory address will increase by 1 byte. Okay, but most of the time for the ARM processor, the memory, okay, we going to push 32-bit data. So for the 32-bit data means the memory will be incremented by 4 byte or decremented by 4 byte. Okay, now moving on to these slides here. Okay, we're going to look at what are the instructions for stacks. Okay, as I mentioned earlier, we have 2 instructions for stack. One is a push instruction. Okay, so this push instruction will save the register onto the stack. Okay, so it will put the whatever value or whatever data inside of the register to the stack memory. Okay, then the stack pointer will be decremented. Okay, so this is the syntax: push register list. Okay, so you can push followed by the register list. RG list to means that registers list lah. Either you're going to push one register or multiple register at the same time. No problem. Okay, and this is the operation. Okay, by looking at this operation, you can see what happened. First, okay, the stack pointer will minus 4. Okay, SP minus 4 means that it minus 4 byte. Let's say like your current SP is at 4008. Okay, so this is your current stack pointer, point to this address. Okay, after you use the push operation, push instruction, so what happened? Your SP now decremented to address 4004. Okay, so this is what happened. Okay, that's why it says that SP equal to SP minus 4. Minus 4 means that 4 byte. You're going to push a 32-bit data to your stack memory. Okay, after you decremented the stack pointer, okay, then after that, push register, okay, value to the memory location pointed by SP. Then after that, whatever value from your register, okay, will be stored inside of this memory location. Okay, so this is what the push instruction do. Okay, let's look at these examples here. We have a few examples. Okay, push R4. Okay, means that you're going to push whatever value in R4 to your stack memory. Okay, this is for single register lah. Okay, let's say you have multiple register. Okay, look at the second instruction: push R0, R4 until R7. Okay, then you close the curly bracket. Okay, so what happened here? So now you're going to push multiple register at the same time. Okay, which is R0, R4, R5, R6, and R7. So a total of 5 registers that you're going to push their data to your stack memory. So in this case, when you have a multiple register to push at the same time, okay, so the highest number register, okay, will using the highest memory address. Okay, means that R7, okay, will be stored at the highest memory location of your stack, followed by R6, R5, R4, then after that R0. Okay, so contoh lah. In this case here, okay, I give you contoh. Okay, assume this is your stack pointer. Okay, this is a stack memory. Address 4000. Yeah, delta. Okay, I put this way. Okay, let's say this is 4000. This is 4004. 4008. 4000 T. And then we have 4010. Okay, followed by 4001. 4. 4001. Okay, so assume this is your stack memory. Okay, and this is the address. And now your stack pointer point to this address, 4014. Okay, this is your stack pointer. Okay, point to this address 4014. And now by looking at the second instruction, okay, you're going to push R0, R4, R5, R6, R7 to your stack memory. Okay, we assume that R0 have this value 1, 2, 3, 4, 5, 6, 7, 8. R4 is, okay, let's say lah, this is A, B, B, C, C, D, D. R5, F, 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 0, 0, 0, 0. R6 is 1, 2, 0, 0, 1, 2, 0, 0. And R7, okay, is B, 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 A, 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 A. Okay, so assume this is the data inside of the registers. And now you have this instruction here, okay, which is push R0, R4 dash R7. Okay, so you have, okay, by looking at this, okay, you have a total of 5 registers. Okay, that you're going to push their data to your stack. Okay, so now your stack pointer point to this address 4014. Okay, after you execute this line here, what happened? Okay, R7. Okay, this R7 here, the data, the content from this R7 will be stored at this address. Sorry, it will decremented first. Yeah? Sorry, the stack pointer will be decremented first, then after that you store the data. Okay, so the stack pointer, okay, decremented to 4010. Okay, so now this is the new stack pointer pointed to this address 4010. And after that, okay, I put this way lah. Okay, so that you can see the difference. Okay, so it will decremented minus. Okay, you can see here, decremented, now it point to 4010. So when 4010, what value that will be stored for? Is it R0, R4, R5, R6, or R7? R7 will be stored first. Okay, B, A, A, A. Okay, and then after that, followed by, okay, 1, 2, 0, 0, 1, 2, 0, 0. Followed by F, 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 0, 0, 0, 0. Then A, B, B, C, C, D, D, and lastly is your R0. Okay, 5, 6, 7, 8. And what happened to your stack pointer now? Is it your stack pointer still pointed to 4010? No. Your stack pointer now pointed to this address. Okay, the less data that you store inside of your stack memory. Okay, so since now you have 5 registers, okay, to store to the stack memory, so you need to minus 5 times lah. Okay, so 4010, then minus 4006, 4004, 4004, and lastly it will point it to 400. And inside of the 400 address, okay, you will store value from R0. Okay, so this is for the push with a multiple register. Okay, so this is why. Okay, moving on to the next slide. Okay, now we're going to look at the pop instructions. Okay, so the pop instruction retrieve the data from the stack by loading a value into register. Then after that, it increasing the stack pointer. Okay, and this is the syntax POP register list. Okay, so the register list, okay, you could put any register lah. Then you're going to pop the value from the stack memory to your register. Okay, and the operation here is first, okay, the register in the register list is loaded with the value from the stack. Okay, whatever value inside of the stack will be loaded to your register. And then after that, the stack pointer is incremented by 4 byte. Okay, plus 4 byte. Okay, why 4 byte? Because we dealing with 32-bit data. Okay, and contoh, we have a contoh here, POPR4. Okay, means that you're going to retrieve the data from the stack, put it to your R4. Okay, and the second instruction, pop R0, R6, PC. So why one? This time, okay, you have a multiple register. Okay, you're going to retrieve 3 32-bit data, okay, from your memory, from your stack memory to this register R0, R6, and program counter. Similar to what we did earlier, okay, since the program counter is the highest register in this list here, so the program counter will take the highest address of the, okay, we'll take the data from the highest address from this stack. Okay, while R6, okay, will take the middle one, and R0 will take the smaller one, smaller address. Okay, we will look at the examples later. Okay, so these examples. Okay, so this is for the single register stack operations lah. Okay, you can see here we have 7 instructions. Okay, the first instruction is LDR RSP equal to OX 400000. Okay, means that now you're going to initialize, okay, your stack pointer, so that your stack pointer pointed to this address. Okay, so this is what happened. Okay, so here you can see at this figure here, okay, now your stack pointer point to address 400000. And inside here, stack pointer have this value. Okay, remember, the stack pointer is inside of our general purpose register. Okay, our not general purpose register, our register data, our register bank. Okay, so here you can see the stack pointer have this address, this value 4000 due to okay the first instruction. Okay, then we look at the second instruction, move R4 hashtag OXAA. So you can see R4 now have a value of OXAA, and then on the third instruction, LDR R5 equal to OXBBCC. So what happens? You're going to load this number to R5. Okay, see here, that's why R5 now we have this value 0000 and BBTC. Okay, and see, this is where your stack pointer lah. Okay, your current stack pointer point to this address 40000. Okay, now we're going to look at the fourth instruction. Okay, on the fourth instruction, okay, it is a push R4. Okay, you're going to push whatever value from R4 to your stack memory. So in this case here, since your stack pointer is pointed to this address, okay, so it will minus with 4. Okay, when minus with 4, it will get this value 3FFFFFFC. So that's why you can see here at this address 3FFFFFC, your stack pointer point to this address. Okay. Okay, due to after you minus the stack pointer with the address with 4. Okay, why 4? As I mentioned earlier, 4 byte because we are dealing with a 32-bit number. Okay, and then what happens next? Okay, after you decrease the stack pointer at value, okay, the stack pointer address, next, okay, you're going to push lah. Okay, data from R4. Okay, what is the data from R4? This is the data from R4. And you're going to put it inside of your stack. That's why at this address 3FFFFFC, you have this value 000000AA. Okay, what happened to your R4 and R5? Okay, your R4 and R5 remains. Okay, no change. Okay, so this is what happened. Okay, after you finish execute line number 4. Okay, the 4 instruction. Okay, on the line number 5, okay, you push another register to your stacks. Okay, push R5. Okay, so what happened? Okay, now your stack pointer point to this address, correct? Okay, so you need to minus with 4. When you minus with 4, 3FFFFFC minus with 4, you will get 3FFFF8. Okay, so that's why you can see here, okay, inside of the stack pointer register, you have this 3FFFF8, and in the stack memory, now your stack pointer point to this address. Okay, 3FFF8. Okay, this is your stack pointer. Okay, what happened next? After you decremented the stack pointer, what happened? Then after that, you push R5. So this is the R5 value. Okay, you're going to push where? To this location. 3FFFFF8. So that's why you can see this address here. Okay, you have BBTC. Okay, so this is after you execute line number 5. Okay, now we're going to look at line number 6. Okay, line number 6 is pop R4. Okay, what happens when you pop R4? Okay, you're going to pop the data, okay, since this is using the last in, first out, okay, the last in here, the last data into your stack memory is this data, okay, the data that I highlighted with this red color here. This is the last data that store in your stack memory. So it becomes the first data will coming out from your stack memory. Okay, so that's why every time you use a pop, okay, so this data here, okay, the data BBCC will be sent to your R4 after you execute the pop R4 instruction. Then what happened to your stack pointer? Okay, the stack pointer will incremented by 4. Okay, so instead of pointed to address 3FFF8, so now it go to this address 3FFD. So that's why you can see the changes inside of the stack pointer register as well as at this location. Okay, your stack pointer point to this address. Okay, 3FFF. Okay, on line number 7, okay, you see another pop R5. So what happened? Okay, so this data, okay, so this is the last data lah inside of the stack, okay, will be sent to R5. Okay, next, what happened to your stack pointer? Stack pointer will incremented by 4 pointed to this address 4000000. Okay, so that's why stack pointer now, this is the value of the stack pointer after you execute instruction number 7, and the stack pointer inside of the stack memory point to this address 40000. Okay, so this is what happened, yeah? Okay, by using the single register stack operation. Okay, single register stack operation means that you push the data to your stack by a single register, or you retrieve the data from the stack by using single register as well. Okay, moving on to the next slide. Okay, you're going to look at the multiple register stack operation. Okay, means that you're going to send the data to your stack memory with a multiple register, or you're going to retrieve the data from the stack memory also using a multiple register. Okay, so this is the examples. Okay, the same program. Okay, like this one. Apart that, okay, now we push and pop the data, okay, using a multiple register. Okay, again, you can see here, okay, LDR SP equal to OX. Okay, please discard the hashtags. Okay, every time you use the LDR, okay, the hashtag will not there. Okay, because you already have the equal symbol. Okay, so LDR SP equal to 0x4000. So this is where you're going to initialize stack pointer. So the stack pointer point to a what address? 400000. Okay, and this what happened. You can see here. Okay, stack pointer point to what address? This address. And inside of your register pen also, the stack pointer have this value 40000. Okay, on the second instruction, move R4 OXAA. So what happened? Okay, you're going to move this value AA to R4. So you can see R4 have this value. And on the third line here, LDR R5 OX BBCC. So, okay, you're going to put this value BBCC to where? To R5. Okay, so this is what happened after you execute these 3 instructions. Okay, after you execute line number 3, then this is what happened. Okay, stack pointer have this value 40000, R4 have this value OOAA, and R5 have this value BBCC. Okay, now we're going to push R4, R5. Okay, you can see here, you have two register, multiple register, you're going to push in one go. Okay, one is a R4 and the other one is R5. Okay, so what happened here is, okay, since you have two registers, okay, means that you need to decrement two times lah. Okay, -4 and -4, your stack pointer. So that's why you can see here, your stack pointer after you -4 two times, okay, after you -4 twice, stack pointer, okay, now pointed to 40000 to 3FFF8. Okay, so this address -4 and -4, or equivalent to -8, equal to this value 3FFF8, and see the stack pointer point to this address. Okay, SP point to this address. Okay, after you decremented, what happened to your stack memory? Okay, the data from this register R4 and R5 will be stored inside of the stack memory. Okay, now, as I mentioned earlier, okay, which address will have the value from R4 and which address will have the value from R5. Since you have two addresses here. Okay, the first address is 3FFFF8 and the second address is 3FFFFC. Okay, as I mentioned earlier, the higher register, okay, will be, okay, the data from the higher register will be saved to the highest memory address, okay, or will be using the highest memory address, and the lowest number register using the lowest memory address. Okay, since in this case 3FFFFC is the higher memory address, so that's why R5 will be stored here. Okay, meanwhile 3FFFF8 is the lower memory address, so R4 will be stored at this address. Okay, what happened to your R4 and R5 after you do the push instruction? R4 and R5 remains lah, no change on the R4 and R5. Okay, then now we're going to look at the fifth instruction, pop R4, R5. Okay, now you're going to pop. Okay, what happened when you're going to pop? Okay, first, we take all the data from this stack memory and put it to the register list. Okay, so now you have how many registers? Two registers, R4 and R5. And so you need to take two data lah. Okay, two 32-bit data. Okay, which this is the first 32-bit, and this is the second. This is the second 32-bit. Okay, the question here is which data will go to the R4 and which data will go to the R5. Okay, as I mentioned previously, again, the highest memory address, okay, will be sent to your highest register. Lowest memory address will be sent to the lowest register. So, by looking at this 3FFFC, okay, the data inside here will be sent to R5. You can see, go to R5, and this address go to here. Okay, next, what happened to your stack pointer? Okay, after you pop up the data to your memory, sorry, not to your memory, to your register, okay, your stack pointer will incremented by 8 lah, okay, +4 +4, okay, you need to +4 twice. Why? Because you have two register, so you need to +4 twice, okay, 2 kali. So that's why now your stack pointer point to address, this address 4000, okay, which is 3FFF8. So this is the original stack pointer plus with 4, and then plus with 4 equivalent to 4000. 0. Okay, now your step pointer point to this address. Okay, they are already there. A location after you initialize the step pointer. Okay, so I think that's it for today. Any question from you guys? Any question from you?
No, Doctor.
Okay, if no question, then I think I stop here. Okay. Okay, so